So Bobby, you want to share some of the logistics, or I'll share some about where we're headed next?
Yeah, well, I'm going to let you share a bit about Plugfest. You guys can step if you like. But thank you all for that session. That was really good. The more we collaborate, the better. We are going to kind of move, thank you. We're going to move towards break. Break's going to be in the Plugfest room with all of our wonderful vendors. And Matt, tell them a little bit about what we mean by Plugfest while we've got the stage.
Yeah, sure. So we are going to move rooms to the room next door. And if you want to know how successful Plugfest is going to be, if you haven't checked out the space, we didn't quite allocate as much space as we've had success in attendance and participation. So I would say you're going to see 4 different RAN vendors, 20 different UE vendors. We're going to test 2 different significant use cases and give you 6 different demonstrations over the next 2 days in 4 couple-hour blocks as we work through the various technologies. I would ask if you're a utility member and you want to be front and center in the show, please get right up front, sit down in those chairs. We have standing room. We're also going to simulcast because we are concerned about space. Plugfest on the WebEx stream. It will also be simulcast in this room. So you can sit in here. You'll be able to hear the commentary, see the tests going on. There's a wide angle camera that'll be showing all of the testing. Feel free to cycle in and out of the room. There's also many different devices that aren't in our little compact Plugfest area. You see active ecosystem devices here. These are demonstration devices. They're wirelessly talking to Anterix infrastructure. There's multiple different demonstrations in various vendors that are in advance of where we're at with Plugfest. So we'll do more orientation once you get in there, but take a break, get a drink, join us in there. And I'm going to try to accelerate the schedule because we've got a lot to go over in a short time. But I think we're supposed to start at 10:50. We'll probably try to start at 10:47, 48. We'll try to speed it up on you there a few minutes. But we'll start with introductions, and from there, come and enjoy a great time and a great show. So thank you. We can make this event unique and deliver value for everybody who is participating. And I didn't want just a traditional trade show. We could all be in this room walking around, looking at UE devices and saying, oh, this is really pretty and it weighs something and it's got lights and connectors on it. That's really nice. Louder? Okay, let's get in from the back. So we wanted to figure out how can we make that happen in the ecosystem. And the idea that was born out of a board of directors meeting, and John and I and a couple members all talking together and pitching this to Bobby, is let's create a Plugfest where we're going to connect all of these devices live in one room at one time and show many different use cases. Al said, is anybody going to participate? And can we actually get this done in time? And I'm here to show you this room is packed. It is full of amazing demonstrations, and it has blown my expectations away of how amazing this Plugfest is going to be. So if you want to see how something works, come check it out here at the front of the room. A little bit of background on how Plugfest is going to work and how this evolved. After we had the idea, we went back to the use cases working group and said, hey, what use cases are the most valuable ones that we can participate in here in Plugfest? And like at a traditional utility control center, we're going to show different electrical schematics, different operating scenarios, and you're going to be able to see in real time, this is a master station, live operating here over the air on various different frequency bands and configurations, and we'll talk you through those, that is going to be issuing and receiving controls. It's going to be communicating across the infrastructure, and then the other screen I want to point you to is over here on my left. We're going to have the success screen where we're going to track through these tests, keep you oriented on where we're at in the test plan, what we're doing, and what's working. And this is the data that we're ultimately going to publish after Plugfest for everybody to utilize. So as the working group committee started working together, and I want to give compliments to Matt Eschmeter on the use cases working group for really driving this conversation and ultimately organizing many of these activities, as well as a couple of other committee members that helped with Plugfest. So we couldn't have done this without Bobby Harris and the events crew setting up this wonderful event, finding us the venue. But then, how do you do working LTE in a hotel ballroom? There's a few challenges. One, we needed a GPS signal. Where do you think we got a GPS signal? We get it 20 stories up off the top of the tower and have to bring a cable all the way down through the building. Those are these black cables you see sticking out of the ceiling here. We all need a GPS cord. So the Ameren team worked very hard, helped us pull those cables up to the roof and get us a GPS signal. So I'd like to call out Brock for his support in that area. We needed testing and detailed testing requirements. So Tom Beddix with Southern Link, with that team, we have an exhaustive test plan that we're going to walk through step by step over the next 2 days. Ron Brady led the technical team in helping us get all of these various equipment scenarios set up. You wouldn't believe the amount of infrastructure and wires that we have laying on the floor back here. So to give you a little bit of orientation to the room and who all the vendor participants are, I want to walk through the room as we have it laid out. So you've seen the 2 monitors. We have 4 RAN pieces of equipment. So over here on my far left, you have Ericsson's core that is running there in that cabinet. It is broadcasting both 900 and CBRS here locally within the room off of those white antennas you see stuck in the corner there. Next to them, we have Nokia, also broadcasting 900 and CBRS within the room, and this is their core equipment sitting on their white platform here. Next, in the red cabinet here, we have Cisco, and they are broadcasting CBRS signal from this white antenna that is up on top of their piece of equipment. And then to your far right, Motorola has their core in their cabinet, and they're also broadcasting 900 megahertz. 900 is coming out of the black antennas you see on the Node B right here, and CBRS off of the white antenna at the top of that equipment. Next, I want to say thanks to Novatech for all of their hard work. Everything that you see here in the middle is their extremely hard and diligent work to bring all of this together, in the sense that they're providing us first the master station that we're using. These are the Novatech Orions that are generating these displays, and they programmed all of the various schemes. And you're going to see throughout Plugfest that we have 30, 40 different scenes and test scenarios that we're going to run for. They programmed every one of those with every different UE device, made them communicate, and have been testing them. I cannot say enough to Jeremy and Sean. I got here Monday at noon. I don't think they've left this room since I saw them Monday at noon. Maybe a few minutes. I think they've slept. Last night, I called them out and said, hey, there's a party upstairs in a really awesome venue with amazing food and free drinks. And there were still 20 people down here testing stuff. That is how committed everybody is to the industry and wants to work together. I mean, think about the fact that we have 4 different RANs and almost 20 different UE devices, and none of them have spontaneously combusted, being this close to each other and working this hard together this whole time. So Novatech also racked up all of this equipment. I'll step over here. What you'll see here in the middle are all of the UE devices. Amazingly, we paint them all black in the utility industry. So they're not the most obvious things, but you can see we'll walk through the various areas. So we have the Cisco devices on the top row in the left rack. We have GE, Motorola, BEC, Nokia, Council Rock, 4RF, Hitachi ABB, and Multitech all provided equipment that are operating. And you might ask, why are there so many different variants of the same ones? Well, we're running a bunch of different tests here. We got a lot of different frequency bands. We're doing failover tests. We need CBRS. While the cores support a lot of different frequency bands, it's typical that a device is only going to be supporting one of those or 2 of those at a time for failover scenarios. So we have different UE devices for different scenarios. The last thing we have, so if we have a master station, it's communicating over a backhaul network, which happens to be some Ethernet switches that were provided here by Cisco. And I want to call out Dan for all of his hard work in getting all of the IP routing and fielding the probably 150,000 intelligent and some not so intelligent questions that I've asked him and other people have asked him about what IP address and who's sourcing this and how is this being added and how does this work. There is a lot of IP addressing going on here. There are a lot of routing issues, making sure we don't have asymmetric routes and all these things happening across all of this infrastructure. Putting all of this in one room was probably not our best networking decision because it made Dan's life a little challenging. And if you want to sit down with him, check out his network diagram and how well he has this network documented and how he was able to make that work. So we have this backhaul network. That is, the master station is connected to the backhaul equipment. That backhaul equipment then talks to each of the four RAN EPCs. Those RAN EPCs have site routers that reach out to the eNode Bs. Those eNode Bs are broadcasting the radio signals that I mentioned earlier. Those radio signals are going live over the air at low power. We're not irradiating you too much. 300 milliwatts of power, and to get it all working here in one room, are all communicating over the air back to all of these UE devices. Now you might say, hey, it's interesting you have all these UE devices, but they could be talking to the power grid. There's got to be something out there. We do have over here in the bottom, also provided by Novatech, some actual UE devices. And some of the things you can see on the screen are these physical RTU devices that would be in the field. So we have a Beckwith DPAC, we have a Novatech Orion IO unit, we have some SEL feeder relays, we have some Bitronic meters, all acting as physical RTU devices that we'll be using. So we have DMP sessions going on from the master station through all of the RAN and networking equipment to those physical devices. But if you'll notice, there's a few more devices on the wall than we have physical equipment for. And I'd also like to compliment them here. They're the ones who wrapped all this stuff up. Can you imagine the table and what a mess the cables it would be? If you want to know what that looks like, just go behind the racks after we're done testing and see all the cables that are back there to make all this work. But many of those cables are actually connected to Orion MXs over here that are acting as RTU simulators. So we have about 40 simulated RTUs running within that device. They're still providing that real-time DMP feedback, and that's what we're ultimately seeing on the screen that's emulated to make this testing work. Does anybody have any questions about what they've seen in all of this space or how all this is working before we start setting up the scenarios and the specific test cases that we're going to start executing? That makes sense to everybody? Got a high level orientation? Okay. Now we're going to jump into the beginning explanation of our first test. And we're going to start walking you through how each individual test is working, what you're going to see. And we'll do this for each test that we're going to work on throughout the day. So we have about 40 some tests to do over the next 2 days. This one will take a little bit longer because we're going to spend a little bit more time making sure everybody's oriented to exactly what you're seeing on the screen. Because the amazing thing about the power grid, it all happens fast when we actually start initiating the failures. So I'm going to call on Jeremy, come up and help show us what you're going to see on the simulator here.
All right. Yeah. Everybody hear me okay? All right. So what we're showing here, this will be our first test. This is a Flizzr scheme. We developed 4 feeders. Those 4 larger red boxes are feeders in substations. And then all the smaller red and green boxes are out on the distribution line. Reclosers, switches, things like that we're going to control. And then each of the letters that you see are a zone in that Flizzr scheme. And so the idea, if you're not familiar with Flizzr, when a fault occurs, we isolate the fault and then restore power to the unaffected areas so we can get as many people back up on power as quick as possible. So,
hey, Jeremy, can we walk through that definition of Flizzr again?
Oh, yeah.
So I'm not sure everybody here knows what it is.
Flizzr is
we throw the Flizzr scheme around.
Flizzr is fault location, isolation, and service restoration. So you locate the fault, you isolate the fault, and then you restore power to the unaffected area of the grid. Anybody questions on Flizzr big picture
So the
idea?
protected relaying devices, the RTUs that we have are physically connected typically to reclosers. They're monitoring the current and voltage. They're programmed, hopefully well coordinated, to trip. And when they trip, they start the communication message to say, hey, master station, something's happened here. I've opened. You'll see that one of the breakers is going to open. Then the scheme kicks in and starts to ask all of the other devices. And this is the key distinction of why we picked this use case for this demonstration. broadband really helps this use case out. You can do this on narrowband communication, but realize for this scheme to work, we are sending 40 to 80 messages and confirmations back and forth on the network to understand that it occurred, assess the state of the system, and then operate the controls. If one of those messages takes too long or fails, the schemes typically lock out and a human operator has to get involved to restore the scheme to operation. Having a broadband network and these things happening in milliseconds instead of seconds really helps a closer scheme out and ultimately reduces the amount of time it takes to restore service to your customer. A typical objective for a closer scheme is that they would take 5 minutes or less so that we can move an incident from a sustained SAIDI to maybe a momentary outage on the electrical power system. We're going to show you these things happening in a few seconds, and this is what you can achieve with the broadband network.
Absolutely. So what we're going to do first is we're going to walk through one of the faults in painstaking detail, I think.
Yep.
So B first. A. All right, we're going to fault zone A. So what you can expect to see is when zone A fails, what detects the fault will be that breaker all the way over the big breaker. So that would be in the substation. A fault occurs. It then opens from the protection settings. All right, so that kills power. Will kill power to A and B zones. And the idea is then we locate the fault, and that all happens in the smart. So once we locate the fault, then we will isolate the fault. So what will happen is that simulated RTU breaker will open, and then we will restore the fault or the power to B using that tiebreaker. So that tiebreaker is open currently, and will then feed that from this other substation. So that's how it will work. So any questions? Everybody good? All right. So we're going to fault zone A real quick. So when we fault zone A.
So can we get it before you do?
Already did it.
Already did it.
All right, we can do it. We can reset it. Reset
Okay,
it.
we'll reset it.
Go again.
I want to get a little chant started. We've been working on this for days. I want us all to chant. Start that test. Okay, everybody want to do it 3 times. Ready? Start that test. Start that test. Start that test. Okay.
There we go. So you see we faulted, and now we open, and then right through there we close the tie and restored power. So what that tested right now is that we could communicate, and what the one no one can see me if I'm over there, right?
That's right. It's got to stay within his
Stay
box.
with white lines. Zone B was restored using that UE. So we know that the commands went through, in this case.
Yeah, let's walk. Yeah, you tell me what you and we'll walk those. So
Yeah, so we went.
we know that there's an RTU. I'm just gonna make it up and say
Yeah, I don't remember.
it's this right.
Yeah.
We're gonna say it's this Switzer 351. That would be a very typical feeder breaker protection device right there. It's on the fault, and it's gonna initiate a message. That message went through an Ethernet cable up here to a UE device. Do we know which one? Okay, went up to one of our 40 random UE devices that we know on the screen. We can figure it out.
I should know. I just don't. It's, yeah, MX2. So
Which one is it next to?
well, it's not going through. Yeah, that one is actually going direct hardwired because it's in the substation where the
Where the RNA is at.
Yeah,
Okay, so running it. So we found out the fault through the hardwire. That then, the master station identified where the problem is needed, and it then sent a command over the wireless network to which UE device?
So the simulated one didn't have a UE. It was not over a UE. But then when we restored power, we went over the BEC.
So here's the BEC equipment.
BEC MX200. So I don't know which one that is. It's one of these.
Okay, one of these 3.
And it's
We're being
running
very
on,
specific here.
it's running on Motorola's 900 network right now.
So 900 communication went up over to the Motorola equipment and back to the core. So everybody got that communication path, and we should have practiced that some more.
I know. First time. So we're going to go through another one now, and we're going to go ahead and reset this speed, and we are going to fault, Sean, C. All right, we're going to fault zone C. So go ahead and fault zone C. We get a chant? No.
No, we're not going to chant this time.
All right. Yep. All right, so we see the fault occurred. We open that, and now we're going to close the tie using the ABB relay. ABB UE over CBRS.
So while we're between tests here, as we're working on tests, I want to talk through why we're building these tests up and we're trying different scenarios. We're showing here that we have ultimately multiple different UE devices, all communicating to the same core. So we've so far had a BEC device, an ABB device,
And this one had a GE as well.
and a GE device,
Yep.
all connected over wireless 900 attached to that core and operating in this scheme. When you see our success results, and I'll introduce here in a second my master's of ceremony in crime here, Mr. Mike Brozak. He is here in the back. I'm going to call him up here so you know what he looks like. But while he's coming up here and we're starting to talk about what's going on, we're going to have a success screen over here that we'll start advancing through that will show you which test we're on and which devices we've been able to interoperate on each different scenario. And what makes Plugfest amazing and interesting is how many different scenarios we are going to be testing here today. And to keep it from not getting boring, we're going to mix up the conversations as we work through these. We're going to step away from live a little bit. Mike and I will be calling out some various different vendors to talk about. I'm going to hand the mic over to Mike so that he can say hi and talk to us about how we're going to engage during part of this conversation to highlight some of the different scenarios.
Hey, thanks, Matt. Hopefully everybody can hear me well. Welcome everyone to the first Plugfest. We have often called this the Plugfest pilot because we've certainly learned a lot along the way. You know, man, I think about your vision whenever you came up with this idea. And one of the key things we wanted to show was interoperability. And that's what we're really seeing here. And that's the reason why we have this myriad of tests in all different bands and combinations, is to show utilities that the products are real, they're here, they're now, and they are fully interoperable. Matt mentioned we'll have a series of speakers that'll come up to fill in some of the times, because and watching the tests go over and over again, we don't want to put anybody to sleep. So we're going to keep you entertained, and we'll do our best.
Yeah, the other thing that I want to introduce here is this is a live Plugfest. I don't expect things to actually work in every one of these scenarios. We are going to, and now we're going to get to the fun part of actually proving that we're not just simulating a bunch of stuff up here on the screen. We're now going to get to the disconnecting and breaking some link scenario part of these tests so that we can show you what happens when one of these devices isn't working and how you will see that on the screen, and then also how we are going to be troubleshooting and testing throughout this. So one of the key priorities of Plugfest is that this is a safe space for everybody to be interoperating and testing. The real value of Plugfest, you guys are getting to see what we call the show. I would argue this is not the actual Plugfest. This is the show at the end to show you that it all works. But the real work has happened over the last 5 months while we've been planning, interoperating, testing at home facilities, and ultimately everybody showed up here for the first time on Monday and started making these devices communicate with each other. And that is the value that showing all of this, you can now utilize and rely on the information that we've established here. And there's been so many learnings that have occurred while different people are working with each other. Hey, if I only did this a little bit better this way. Hey, can you do this way? We're seeing devices that we haven't seen this chipset talk to this chipset before. Oh, we need to make a tweak to this configuration. There are so many engaged parties in this room that are all making sure that their baby is working as clean as possible to show these tests. And those are the real learning events. So now, when you're back at your home utility, when you're deploying your pilot or your operational system, we hope that it just works out of the box, and some of that problem has been taken care of by Plugfest here today. So as we move into this next test, we're going to show you a communication failure.
You want us to?
I would love to see communication failure. So somebody doesn't say, hey, Matt, all I always saw was some simulated screens on a TV screen. This surely isn't that complicated.
Want to reset? We'll pull a Ethernet cable.
Yeah, we're going to disconnect an Ethernet cable to a UE device. So we're going to disconnect the connection from the UE to the recloser. I don't care, whichever one is operating. So we're not going to disconnect the UE from the network in this scenario. We're just going to connect the UE as if it lost communications connectivity to the recloser. Jeremy, you want to describe what they're going to see on the screen before you do it?
Yes, you should see a COM fail show up on the screen under that UE, and it'll flash and show that we are unable to communicate to the RTU at the end. Doesn't mean, and we don't know why at that point. Obviously, we do know why, but in reality, you might not know why. It could be power loss, could be RF, could be an Ethernet cable, could be a bunch of things. So I just got to figure out which one to fail.
And so how they're detecting that is the master station is monitoring the real-time DMP sessions from the master station out to every UE device. And if it fails to get communication, so when we showed up on Monday, all these showed was COM failures. And as we built the network, as we brought on different RAN providers, we were able to bring on the various pieces of equipment.
So now you can see we just pulled the Ethernet cable from this GE Quad 2, and it shows that it can no longer communicate. So proving that we're actually not faking this out.
Okay, now we're going to restore that connection.
Yes, we are.
And in a few seconds, you should see that COM fail, as soon as it restores DMP session, you should see that comes back. And that should take a couple of seconds. We're polling every few seconds. Since it's attached to the network, it shouldn't take too long. Remember that this part is live testing.
Unexpected test.
That's right.
Never go off script.
Never go off script. You should see how long it took to create the script. And
there.
Yep, you'll see that the COM failure has gone there. So here we're just summarizing, showing that how something would look, how you'll see it if it does fail. We will probably absolutely see some COM failures during the middle of this as we test different things. We got a lot of different RANs and a lot of different Spectrum bands all working in the same room. And if we have a challenge with one of those, we'll see it, but we'll take a second, we'll troubleshoot it, we'll get it going again.
And as a side note, if we do have a COM fail, we won't test that area because the way Flitzer works, if you can't see the state of a breaker, it locks out that zone surrounding that. So right now we don't have any COM fails, everything's up to talking, so are we doing a few more tests?
Yep, we're going to conduct a few more tests.
Awesome.
Yep, let's move on.
All right, we're going to move on to the next one, which will be.
And Mike, can you put up the success slides and advance them so we can keep track of where we're at in this particular test? So we're on 900 megahertz with Motorola's RAN. We've done run 1, so we've seen BC, GE, and Hitachi ABB, and Nokia's equipment.
Well, we're not done with run 1 yet. Run 1 is pretty big, and run 2 is pretty big. So let's go ahead and fault the next, which is zone D. And that'll be testing that quad 2 as well as the BBC. So you see those worked again. Good. Reset.
So we're going to do one more test here, and then I'm going to ask Motorola to come up and talk about their RAN solution while we continue. We'll keep running the tests here in the background, and if we see something anomalous, we'll cut live back to the testing, and we'll diagnose what's going on there.
All right, we're going to fault zone G. And that tested the ABB on Ericsson CBRS. It worked beautifully, and
yeah, so we'll keep testing. You guys keep running through tests here. I'm going to call up Fred Christoph from Motorola to highlight for a couple of minutes. Standard warning, couple of minutes, 1 or 2.
I was told by Mike I had 30 minutes.
That is incorrect.
No, I think you did a great job of describing the RAN core. I'm not going to get into the details, but we have 2 of our best engineers over there, Gino and Marcelo, stop by, ask questions. They know it inside and out. Right after this test, we're going to do something kind of unique. We're going to do a test that shows how we can do multiple carriers inside of the 3x3 by leveraging the 1.4, a narrowband IoT, and another 1.4, all in the 3x3. So So stick around for that after that. And we also have our booth over there, right around the corner. Couple of things at our booth. I think, you know, when we designed our core, our RAN really focused on utility grade, right? And what does that mean? High power, right? We'll talk a little bit about that at the booth. LMR, LTE, coexistence. Got my cheat sheet here as well. Video. We're going to show a video going over a 1.4 as well, over 900 megahertz. So start thinking about the use cases as we can do more with the carrier. And the other thing is we've got a lot of devices. One of the things we really focus on is LMR and LTE interoperability, how they can converge down the road. Thank you.
Yeah.
Keep it to 2 minutes.
Thank you, Craig. I appreciate the commentary. I will say, you know, right after we conclude this round of testing, Motorola is going to go into depth and show, and I'm impressed by using every bit of the spectrum by using 2 to 1.4s and a narrowband carrier in 3 megahertz of spectrum. That means we're using every last square inch of it. And that's something that I think some of us will be interested in seeing. Now that we're back to live testing.
Run 1 is done and everything tested and passed.
Awesome. So can we give, oh, Mike's already on it. He's already got our checkbox over here. You can see how many different UE devices and vendors we've been able to get tested so far. We're going to continue testing, and I'm going to ask Mike Wadey from GE to come up and talk about their UE devices here. Thank you very much, Matt. First, I want to take a couple quick things. First and foremost, I'd like to thank the vendors. I've never been in an organization before where there were multiple vendors working towards one common goal, and this is the output of that. Second, I'd like to thank the Novatech team for putting an incredible rack together behind me that includes all of us, so we can have a live podcast, and then also Bert's and Matt and the other vendors that came to the table. I'm Mike Whiteley with the GE MDS team, and we're in the booth forward from where we are today. In the rack behind me, we have actually a quad dual modem quad SIM MDS forward unit. Actually, 2 of them operating in these couple of use cases, and they also have FirstNet backup. In the booth today, we also have some HPUE options that can improve your RF signal out to the edge of the network. So stop by our booth and take a look at that. I'll also mention that AT&T across from our table is also showing a live version of the HPUE with the airplane antenna, so that you can actually see the difference between a standard commercial RF communication and what you get with the upload with the airplane HPUE. Thank you very much. Thank you very much. I do want to highlight, why is it important that we're talking about why is it important that we have a quad radio UE device? Does anybody know? We'll make this a little bit user interactive. Questions, comments from anybody on why it's so important to have multiple radios in one UE device? Any feedback? Anyone going to blurt out? I'm going to call on Dewey here, and he says redundancy. Absolutely right. Think about the fact that we can now have private infrastructure that is our primary carrier, and for relatively low cost, since we're not using it very much, we can have public carrier that we're also communicating across. So by leveraging the international cellular standards and being part of a worldwide industry standard, we can now have one UE device that can participate in the network in multiple different ways. So there's kind of 2 scenarios with that. We can either have one modem and 2 SIM cards, where if you lose carrier, you're going to have to reboot. And we're introducing here the failover tests that we're going to do later in the scenario. After we finish all these interoperability tests, we're then going to focus on failover and show you the 2 different networks, or the UE devices moving from a private communication to a public communication network. That's one scenario. You can also, if your application requires it and you want faster time, so if you're going to switch carriers, you usually have to change the modem profile, and that usually takes
seconds because you don't have to reboot the whole device, but you have to reload the profile that's running on the modem, give it a new frequency band, let it get a new SIM attached to the network. That all takes seconds, 30, 45, 50 seconds in most cases to happen. That's amazing. If you would have considered that we would have invested in network, and if we would have lost our infrastructure for whatever reason, natural disaster, we're just doing maintenance, something happens, we don't have coverage in that area, we would have just been down. And we would have had to explain to our utility partners why we're not providing them service. Here, in 30 to 40 seconds, you can fail over onto another network. Now, some of the tests take a little longer than that because there's multiple hold-offs to make sure that we're not doing it too aggressively. We'll show those tests in a little bit. If you put multiple modems in there, which they can have 4 modems in there, you can avail yourself of multiple different public networks. So that could be, you could be on narrowband, and if narrowband isn't working, go to broadband. Broadband isn't working, go to a public carrier. You could have 1 or 2. You can have multiple different scenarios. And the product is modular. You can change the configuration of each one of those devices. And because having multiple modems means they're up and active, then it's just a route switch change to change networks. It takes a mere seconds. Basically, how aggressively do you want to program your routing algorithm to switch paths? So you can have failover in just a couple of seconds. So come back to the live testing and get a status update on where we're at here. I think everybody can see we have a couple comp fails. Okay. We don't know why right now, but we are testing around those with no problem. And those actually were tested yesterday. So we know they work, but right now he's testing zone L. So we're going to continue to run through the test plan, so we're not losing time here. We have 2 that we're still going to have to go back and diagnose and fix. We'll get back to those in a little bit as we figure out what is going on with the various communication paths. But it's reality. That's exactly how it'd be in the real world. This is the real live aspect of doing testing and learning, figuring out why is this occurring and what can we do better about it. I will highlight, one other amazing, I think, first that I haven't seen anywhere in this Plugfest. We are operating CBRS on 4 different EPCs at the same time. If you're not familiar with what CBRS is, I'll give a little bit of background on that. So this is 3.5 gigahertz spectrum. It is managed by a SAS, a spectrum access system. These devices are all reaching out and communicating to those SASs in real time. In this particular case, we have 4 vendors, and there are 3 different SAS providers, and we're using all 3 of those different SAS providers. So not only to make CBRS operate in this room, are we doing it with 1 SAS provider coordinating our frequency, we are coordinating across 3 SAS providers. They're all interoperating with each other to provide us spectrum for the CBRS operation. That's something else I have not seen. It has been successfully working with a few challenges. We always managing our spectrum is always a challenge. The other thing that I want to point out, we have a very simplistic, the other reality is I'm going to step off camera here for 1 second and grab our token system. So if you ever want to know which 900 megahertz provider is actually transmitting, we had to come up with a very simple process. So if you don't have this water bottle, you're not supposed to be broadcasting 900 megahertz. You notice sort of setting on top of Motorola's phone, we kind of have it behind the TV. You can't see it there. But if you see this water bottle moving around, this is the all-important talking stick. This controls, or at least identifies who is supposed to be operating at 900 megahertz at that point in time. Sounds like a simple thing to coordinate. It's one of the things we had to implement at Plugfest. How are we going to monitor this? Yes, there's a question? 1 second. Okay, we got a question in the audience. I'm going to hand him a microphone so everybody can hear. For the CBRS, for the different SASs, was there a difference in the grants coming back from any of the SAS providers? In this case, we pre-coordinated so that we did not have to, hopefully, deal with any challenges of the grants. And we coordinated on what channels we're asking each person to come up and configure on, and they got that grant back. However, I will say, we had a little bit of miscommunication, and we were using 10 megahertz carriers in CBRS, and one of the channels got enabled at 20 megahertz, and the SAS did exactly what it was supposed to do,
and it signaled that there is a challenge here and forced a change in the system of the other channels to push the system around. And that is one of the things we had to troubleshoot yesterday. So while we didn't get an initial response to that, we did see a change. One thing that I learned yesterday is that the multiple different SaaS providers only communicate once overnight. So it was very important that we got all this working yesterday, or else you would not be seeing CBRS today, because that coordination had to happen overnight between the three different SaaS providers. So again, digging into one of the technical lessons of things that we learned here. I'm going to check and see what's going on the screen here and call on Jeremy here in a second to explain what we're seeing.
I wasn't listening, sorry.
I caught Jeremy off guard here. He's solving the problems. I was just gonna, as we transition from one question to the next, I was asking where we're at with testing and what are we seeing right now.
All right, we've again, we have some troubleshooting we're doing to figure out some of the comp fails, but we just tested zone B on this one, and that was testing the Council Rock modem. Worked beautifully, no problems at all. So we're just troubleshooting right now on this one, but so far everything has passed. And we knew this one was actually up and talking just a few minutes ago, so we know it works. It's just, I don't know, maybe we had stepped on something. We'll figure that out, but everything's it's
The challenge with all the cables in the back is you don't break the cables.
So we are done with the 3 runs of the flip. We've tested, except for the one that, we're going to retest again, but they've all been tested prior to this anyway. So we know they all did pass.
Yeah, so now that we're finishing up on run 1 here, we do want to go to a Q&A session. So we've already taken one question from the audience. There has to be more. I see 100 people standing around talking, so there has to be questions being asked and discussed. Does anybody have a question here in the room? And just as a safe space to break stuff because it's actual testing, a space to ask any question that you would like. We're happy to dig into it and answer it.
What sim ranges are you using for the cars? But the HSS.
That's a great question. Let me find an expert to answer that question. Do you know, Jeremy?
Like sim ranges as in
The
which,
IMEI range numbers.
no idea.
But I will.
Each infrastructure vendor provided their own, and then AT&T provided AT&T Business and FirstNet, and then US Cellular provided cards. So
Yeah, I'm going to
you have
get
to ask each one probably.
a slightly more detailed answer to that question because that was one of the big coordination factors that we had to do. But yeah, each vendor provided their own, network ID as well as their individual range. However, I'm going to call on Matt here in the back to see if he wants to opine on. Don't mind the man in the green shirt in the background. This is Matt Eschkeiner coming live to you. Hopefully, we can answer a question about IMEI ranges and how do we coordinate it because there were a few coordination details that we had to do because we do have some overlapping space.
Yeah, so the view up front side, we had to have a strategy for handling multiple PLMN items, which is the mobile entry code, mobile network codes. There is a standard within CBRS that says that use 315010. The concern we had, if everybody showed up with that same PLMN and you're using it on your hardware, and there would be modems logging on the wrong days, wrong networks. So we agreed to abide by the ITU standard, and it says if you're in a test environment, you can use the country code as 999. And some vendors did that. One of the vendors jumped the gun and they're so smartly picked a small self-specific island and assumed that they won't have any collisions with that PLMN. So that was part of the strategy. We ended up using 4 different PLMNs. We got what we needed to be, just it was a little interesting how we got there.
And maybe get a little commentary on what is a PLNM, and I'll take a initial stab at it, and people that are much smarter than me can expand on it. So every UE here has to have a number assigned to it, and that number is made up of multiple different parts. The first part of that number is your country code, 3-digit number assigned by, I believe, ITU. Worldwide, every country has different country codes. So if you look at the IDs, most of them in the US use one country code, but I think we're now onto a couple of them. You then also have the network provider ID. That's another 3-digit number that is assigned that every one of us as utilities are going to have to go out and get registered. I might actually call on a few active utilities that are in deployments for them to talk about. So giving Ameren, and I see Omar is getting awful close to getting called up here since he keeps walking closer, to describe the process they went about registering to get their network ID. But that is, you can think of it as your carrier ID. So T-Mobile, Verizon, AT&T, each have those. If you're ever super really nerdy and you ever go into your phone, you can usually do a scan and see all of the network IDs. You actually see that the carriers actually broadcast multiple of those network IDs. For example, you might have one network ID for narrowband IoT. You might have another network ID for your broadband channel. And that number is then concatenated with, I believe, a 6-digit number to finish it out, a long random number that is specific to that SIM card. All of those bits together create your IMEI number, I believe. That is your unique device identifier, so that when you register into the network, you know where in the world, and this is how roaming works. When you register into that core, if that is not your home network, it can look in the global routing table and figure out how to get you to another provider. That's how you can take your device, and that's how we can roam onto another service provider. So, Omar, do you want to add anything to that, having actually done that process? Omar can't even hear me, so he's not going to answer my question. I think that's a story, but we'll go with it for now. So there's a little bit of background on IMEI numbers, how they get assigned, how we go about using those in this network, and that is absolutely one of the things that we've had to coordinate. And it's one of the things that you need to be prepared if you're going to deploy a network. Registering through that process, getting that, and assigning those is an important part of the process. I'll add an anecdotal note to that. It sounds simple. You're going to put a bunch of this information in a SIM card. The challenge is we usually order them like hundreds of thousands of cards at a time. You make little mistakes in that, and you have hundreds of thousands of cards. You get a handout here at UBBA because they're not going to be worth anything on your network. So it's a key step to getting your network up and running, and a lesson that you can learn from several of the utilities that are now executing in the space. So,
Want an update?
Yes, I would love an update.
All right, we got we corrected the issues for the 2 devices that were offline.
Okay.
And just tested them and are in the process of still testing them, and all good to go.
Did we learn anything and why they were offline, or was it
Sure
a dumb idea?
Yeah, it's just little error.
Okay.
It happens. So nope, everything's now done.
Awesome. Any other questions before we call up another vendor? It's got to be another. Yes, let me get you a microphone. Can I grab your microphone? Sorry.
Are any of the utilities making headway on eSIM?
Are any of the utilities making, and I heard I was going to say something so I can think about the answer. And I will say I don't, it is discussed. I will call out to people who are working on utility networks. Omar, you want to answer this one? eSIMs, any progress on eSIMs at SDG&E? It says not right now. Ameren, anybody active in the Ameren deployment that wants to come up here and talk about Esim Technology? I will again call on the man in the green shirt, the mystery behind the curtains, maybe Matt Eschbeter, to talk about generally what we're seeing. Is definitely something active in the conversations about network design, about what we're doing with eSIMs. And a little bit of background, does everybody know what an eSIM is? Everybody know what a SIM card is? We talked about the IMEI card. If you have a cell phone, there's a little plastic chip in there. You know what that little chip is really good at? One, it has an authentication token, an encryption key that's used to authenticate you to the network. 2, it has your network identification number. 3, it has a bunch of configuration parameters on it. 4, it's kind of a pain in the butt to distribute all of these little pieces of plastic. And so the industry has come up with Esim technology, which is, it's still a SIM chip, but it is physically burned onto or soldered onto the motherboard of the UE device. So you don't have to pull the chip in and out. Although that creates a new problem, which is how do we get all of that important information, like your network ID, your configuration, all those details, onto that device? And the process generally is you will get your SIM on a sheet of paper that we print it out, and there'll be a QR code on it. And in that QR code is enough information for that SIM, or for that device, to really get the address of a server out on the network where it can go get all of that information, set up a secure session. So there's some tokenization that's occurring. Set up that secure session and download from an eSIM management server all of that configuration details that is needed on the network. That will be massively important. Does anybody know why this is such a big issue for utilities? What is one of the biggest use cases we have for utilities when it comes to saving money, and one of the things we talk a lot about? Just cutting down on the amount of windshield time. What's really bad that happens if we need to change all of the SIMs in a whole bunch of devices? A whole lot of this here windshield time. So one of the ways that we can manage that is if we can get those SIM devices talking to one of these servers, we can have a zero-touch provisioning process where they can go out and get that information live, and we can continue to update the configuration of those SIMs. So that's the genesis of eSIM technology. I shared a lot about it. I'll call on Matt. Do you want to add anything to that conversation? I need to get the microphone back.
Sean had something hard to say, but it's early on for us. One thing that's apparent, it's a very carrier dominant technology today. We're working with a small shop to talk about strategies for eSIM delivery, SMTP, and kind of detail. One thing that doesn't change, the complexity of getting that SIM profile right still remains. You can't just deploy eSIM and expect that all that complexity goes away. The cost of being wrong is a little less because you can make mistakes and do it again, but it doesn't relieve one of the biggest burdens of SIM deployment, and that's to get the profile right. There's just a ton of parameters. And from a further background for a couple decades, burned tens of thousands of cards incorrectly, and we're going to try not to do that with eSIMs, but we're looking at it. It's interesting and it's important.
So if you haven't experienced eSIM technology yet, you can, if you buy one of the latest flagship devices, a lot of them have 2 SIM slots. Usually, not always, one of those SIM slots is physical, and now you're starting to see in the latest generation, the second one being an eSIM, a virtual one. What's cool about that? You can have now one SIM chip in your phone to manage your voice communication and effectively be your phone number, and it can provide you a data connection, but you can potentially also, this is a much bigger deal in Europe where countries are smaller and you have multiple different networks. You can put a second SIM in there for global roaming or data access to a different network in that second slot, and usually save yourself some money on data access costs. So it also allows you to have kind of dual profiled devices. So in theory, you can now carry one device that has a complete profile, including separate phone number for work, and a complete separate profile for your personal life. Both virtualization in the phone and your service can be kept differently during that time. Okay, with that, I'm going to call Michael Henniker with AEC to give us a little bit of background. You saw his devices. I'll say at the beginning of this, thanks for stepping up to the industry. I was not aware of AEC before Plugfest, so definitely stepping out in the industry and showing the devices. If you want to share a little bit about your product and what makes it unique and why you're excited to be here and whatever else you'd like to say for a couple of minutes.
Sure, thank you very much. Esim Technology is very happy to be here and glad to meet so many wonderful people. You see, we've done some testing in the Plugfest. We were the first test that they did on the Blizzard. BEC Technologies has been in business for almost 50 years, with the past 15 years in cellular. So we do a lot of different modems. We do a lot of form factors. We have indoor and outdoor units. We have units that are for fleet management. Here's our group right here that we demonstrated here at the show. And we really look forward to maybe come visit us at our BEC booth right over there. But BEC Technology is a manufacturer, designer, developer of these products. And we also support them, we engineer them, and we help you on the other side. Once it's deployed, we have a really nice element and network management piece that you can find all your devices and look at all their performance and information on the RF side. And we are also certified with AT&T, T-Mobile, and Verizon on many of our products. So we really have a lot of different solutions. We are working with utility operators, a few of them already now. If you look at the fixed wireless access world, where maybe some of your utility lines run through, we are the #1 on the market for fixed wireless access with independent telephones. So if you're in a rural area, there's a very good chance that we have networks there already that are certified with those operators, as well as the big three. Is there any questions you have about BEC? Anybody? I would say if you take a look at our product, it's a fairly simple, lower cost device that's industrial grade and certified for that. We do have units with single SIM cards as well as ones with dual SIM cards in it, depending on your needs. And I think if you look at what differentiates us, it is not only our support and service, but if you take a look at our software that we have that goes with the modules, it actually shows you where it's placed, how far away the device is from the tower, and it gives you a representation. We're out running with that BC Central as a controller. We're running with that right now. You can take a look at it. So that's probably our unique capabilities. And the other thing is that we are very good at designing specifically for you, so we can manufacture based on your specific needs. And BEC, because of our industry background, we saw a couple of different bands here. If you look at 700, 800, 900, 1900, I mean, all the bands that are being used in the US, very likely we can find a solution for you in those cases where you need to have combination. Thank you very much. We're really happy to be here.
Thank you, Michael. I really appreciate it. Okay, so at this point, we have finished test 1, 2, and 3 in the test plan. We've showed interoperability with all of the devices in the first column. So to reiterate, we were operating at 900 megahertz with Motorola as the core, and we tested all of the UE devices in that configuration. We're now going to go to the second part of our testing scenario where we're going to talk about failover testing. And in this area, I'll start to set up the conversation. We're going to have various devices, and we're going to this time be looking at individual UEs, and we'll have a screen up here. We'll pull it up here in a second, where we'll show you each of the motor manufacturers. We're going to show you the primary network that they're on. In this case, it'll be 900 megahertz Motorola. And then we will be failing over onto a public carrier. We have various different public carriers I mentioned earlier. US Cellular, we have FirstNet, AT&T Business Services. Those are the three public carriers that we're going to be cutting over to. So in those scenarios, there's a really amazing aspect of this configuration. Normally, if your field device was to switch networks, what is the first issue that you run into when you're deploying RTU devices and multiple different networks? Anybody think of a common problem? The IP address changes. Does everybody know how hard it is to change an IP address on an RTU device? It takes a mere second to change the IP address in the configuration. Does anybody know how long it takes to usually do all the testing that the control center wants us to do once we change the IP address? That can take hours in some cases. So changing IP addresses is very challenging for us. An amazing thing about this technology, we're going to switch carriers here, and because it is a tunnel technology through a data bearer, you're not going to see that IP address that in-device change. You're going to see it go offline for a few minutes,
But we're going to switch from a private network to a public network using the same security model, using the same encryption, using the same IP address. And you can do this to as many different communication carriers as you want. You could have multiple private networks, you have multiple public networks, all interoperating in the same system. So with that, I'm going to see if the man behind the curtain is ready for our testing and call on Jeremy. He says, I got to stall for 1 more minute. He doesn't have a mic. Mr. Brozak, here comes the mic. All right. Ooh, wow, that was loud. All right. We're going to do a failover test. We're running a few little things here. You want to switch over that? All right, I'll explain this screen a little bit. We already had one failover. To go back is a little complicated, but the idea is you can see test 1 we're going to run. We have the vendor UEs listed, and then a primary band and secondary band. In this case, the primary band is 900 on Motorola, and then the secondary bands, we've got CBRS on Nokia, and then US Cellular for 2 of the UEs. So the way we're going to do this test is Motorola is going to fail their 900 so that it is a reality that would really happen. And then we're going to watch as the UEs fail over. And the way we're testing this in the background is we are polling DNP again, and then when we can't get a response from a UE, we start and switch to polling on the public or the other network. And so some of them may come up fast because they have the dual modems. Some of them will take a little longer because they're single modem. So I'm going to have you guys fail 900. Yeah, so we're going to Motorola is going to administratively shut down, simulating the loss of the eNodeB. This could be failure of an antenna, feed line, one of those things, but we're not going to give the UEs a head up that they're going to lose their registered carrier. And so each of these UE devices is going to have to detect that they lost connectivity. And by powering this down, it's a little bit better than them sending a disconnect notice. So the Motorola just said they shut their system down. Yep. So it'll take a few seconds for us to notice that we can't communicate. We have some timeouts in there. Yeah, we're simulating that this is an actual failure. So normally if you did this in an LTE network, it would actually send a disconnect, an unattached notice to the UE device and say, hey, get off my network. I need you to go somewhere else. That gives the UE device a little bit of heads up. In this case, we just cut it. So the UE devices now have to detect that. How do they detect that? There's multiple different ways. They can monitor the modem and see that they're not seeing the hello message that they're expecting from their base station. They can also, in many cases, be set up to monitor some centralized IP address like your EMS server. And if you can't get all the way back there, you might still have an LTE connection locally, but if you can't get through all the backhaul and the firewalls and everywhere back, they'll detect that failure. When they detect that, they'll go ahead and switch over. Different carriers have different scenarios, something that you can investigate with each one of them. As they detect those failures, they are then going to, as I described earlier, reload their modem profile and switch over to Nokia's. So in this case, we're going to be coming over to this white box right here. They're going to be reattaching to this white box and reestablishing data communications. And you heard Jeremy's explanation of how the communication is going. And you can see the testing kind of occurring here in real time. They're working their way over. The first 3 are up on Nokia CBRS. We're looking why we think we're still communicating on the other. I think that's a potential error on our side. And then for RF, we're waiting. Seeing the green up there went down. Oh, there it went. Sorry, that was a time thing probably on our side. It's in how we set up the master station to monitor the test, not the testing itself. No. So 3 of them are back out, and we'll see the other 2. We'll come up hopefully pretty soon here. So we've had failovers between 2 cores that are within this room. So from Motorola to Nokia. Well, also some of the UE devices are going from Motorola out to US Cellular onto a public carrier. So we're showing both different scenarios at the exact same time. Yeah.
Yeah, so Dewey asked a question, are we ever pulling on the backup network to make sure it's available? So that question depends a little bit on what the device is and how it's configured. But if it has dual modems and dual data sessions, then
We can. If we just have to write it the right way. You have to, the RTU also needs to support it on the other end, multiple DNP sessions. So, yeah, you can do it depending.
if it's a high availability scheme, you would definitely want to monitor your secondary channel. Now, Jeremy just mentioned a key aspect of that. Sometimes DMP master stations don't love having simultaneous redundant communications going on at the exact same time. That's starting to get more widely supported in the industry. Another thing that is often done is if you can't monitor the backup DMP session, we can monitor the backup data connection to the device, either through an ICMP ping or by monitoring the IPsec tunnel. One downside to a lot of monitoring, depending on how reliable and important it is to you, a lot of the backup channels are trying to minimize the cost, especially if it's a public carrier. And I could spend more of your money keeping up IPsec tunnels on backup cell modems than you would spend on potentially a commercial service normally, because if you bring up that IPsec tunnel that's sitting there doing hello packets all the time, we can tune that down to lower that amount of communication, but it usually comes at the cost of time, how quickly it can get going again. So I can't see screen there. We're still waiting. This test would take up to 5 minutes to execute. Slash will ask if everything's going fine in the background. They can watch the data connections. I see Furious typing back here on multiple different command lines, monitoring IP addresses and such to see what's going on. But have no fear, these tests do take a long time. So Beck, any other questions from the audience that we can answer? With that, I'm going to call on Mike and see if Mike's got another couple of minutes. We're trying to get another vendor. If there's a vendor who can hear me that has a UE up here that would like to talk for a few minutes, come up and say hi to Mike. Okay, we've got Hitachi up here, and who is it Joe? Hey, Ron. Good seeing you. Hand you a mic here.
Thank you.
You want to give us a little rundown on what we're showing here? Sure. Maybe update everybody on the branding, since we all know ABB in this space, but the Hitachi aspect.
Thanks, Matt. Great question. Yeah. So on the branding front, we're up until October.
Yeah, use the microphone.
Hitachi ABB. We've now become Hitachi Energy. So over time, you will see the branding change in the portfolio. But what we have here is our TRO 600 series of products. So this particular product is the TRO 620. Supports not only what we call it as the options at the edge device. So it supports all of the standard cellular bands, including FirstNet, as well as the various private LTE options. So we've got a CBRS version, as well as an Anterix version. So both are on display here. The device itself, it's a fully managed option at the edge device. So we've got a full network management system that is available to support this. In this particular application, as everybody's talked about, running BNP3, and so we're taking advantage of the utility protocols. Part of our whole portfolio, we not only have cellular in the product, but we also have private options available. So there is a broadband mesh technology that's available, as well as a narrowband technology. So when we think about rolling out these networks, it's important to make sure that as the private LTE network rolls out, if you get into an area that there's not coverage, that the utility has an opportunity to deploy a product already there. So with this, you can deploy on commercial cellular, or you can deploy using one of our private broadband or narrowband technologies prior to the private LTE spectrum becoming available and the coverage in that particular service area. This is the first of several products in our TRO 600 series. We'll be coming out shortly with a small form factor device. as well as outdoor hardening. So you'll see as we evolve, and if you stop by our booth, we've got a 610, a TRO 660, and a TRO 670. So excited to be participating in this event today. And it's the beginning, it's not the end. So
Thanks for sharing on it. I pointed out when I walked up, and something that I noticed is the green connectors and some of the unique wiring configurations that they support, both for serial communication, not from direct analog to digital as well. So it doesn't all just have to be this talks Ethernet or serial to some other device. You have the ability to talk to a few things locally. Can you comment on that?
Absolutely, and I think a big part of our portfolio is understanding that we have to support devices that are 10, 20, 30, 40 years old. So we not only support forward-looking technologies, but we do support analog and digital inputs, and we support Ethernet through our serial options, whether it's RS-232, RS-45, fully flexible, forward-looking, and supporting legacy devices in the field as you need to add resiliency and redundancy to your modernization strategy.
Yeah, thank you very much, Ron. I appreciate it for sharing. And while we've been sharing a little bit of information with you, going back to the test area, you will see, I got to read which one. The Cisco IR1101 has switched over to US Cellular.
And 4RF did as well. And now we're troubleshooting why it doesn't show that. But we did see it shift over for a little while. So everybody did switch over.
So with that, this concludes the first failover test. And now we're going to start. Are we going to go to failover test number one?
This is it. This is the end.
Let me check my timing here. 12:02. Now we're going to get all a very nice emergency warning. I hear the first one's coming into cell phone, so let's launch that propagated throughout the room. Okay, yes, there's a question. Can I give you a microphone 1 second?
Make sure it's on. I'm going to turn it on.
A question about the two devices on the bottom. Those are single modem? Those are single modem devices? Just that one? And it still took 5 minutes to. Okay. Just want to talk a little bit about why it takes longer for a single modem to switch from.
Yeah, I can talk about several different parameters. One, when we sit in this room, we say, oh man, this takes forever. This is completely unacceptable. However, in most use cases, in the time that it takes this thing to switch over, I can't even recognize and respond as the utility that something is actually happening. There are a few applications that are high sensitivity, and that's where we go to the dual modem devices. Let's walk through all of the bits that contribute to this time. There's about 5 or 6 things that are happening here. Keep in mind, we're monitoring the highest level of communications, or the highest level of the stack, the DMP messaging that's going on here. So the first thing that happens is when we power down a carrier, the has to detect that. That's usually a highly configurable parameter that you can configure in the modem. And it's this question of, do we want to ride through a situation, or do we want to put it on a hairpin trigger where we head down a path that might take a longer amount of time? Many of these devices out of the box will be set to a couple of minutes of loss of carrier before they're going to initiate the cutover, because they know that that's a disruptive process to a significant part of the infrastructure. Essentially, the IP address is moving, the master station may be moving, there's lots of different things. So we typically have that timer set rather high. We ask that they lower that timer to 1 minute for testing, because we don't want to sit here for 5 minutes while that fails. So that's the first thing that has to happen, is detection of loss of failure. You can do that looking at RF factors. You can also do that by using, typically, you can monitor some sessions. So if you're running BGP or IPsec or one of those protocols, you can monitor those protocols. You can also monitor, most of them will support an ICMP session to monitor some master station. And the cool thing about monitoring an ICMP is you can reach way through the network and say, oh, monitor my master station. My master station isn't working. Then flip over, and you could have lost all kinds of infrastructure in between. So those are all the 3 scenarios where you detect failure. And at that point, we've consumed from probably the lowest I've ever seen it set to 1, highest maybe 15 minutes, depending on the application. So there's that time. Now, the modem is detected that there's a problem, and it's going to take action. The first thing that it has to do, if it's switching bands, and it is a single band device,
is reload that. The modems are mostly software defined at this point, and you completely have to effectively reboot just the modem, not the entire processor, and give it a totally new profile. So in FPGAs, they got to switch frequencies. They have to change their up-down configuration, their symbol rate. You might even be changing protocols. That you might be going from a GSM base to a CDMA base. There's all kinds of different changes that have to happen in that. That usually takes 30 to 40 seconds for the modem to reboot. Once the modem is booted up, then it's a standard attachment process. It has to register to the network and get a bearer channel, so a data channel. That can take a couple of seconds on the good time. It can take tens of seconds on a slow time. You might see this on your cell phone. And when the screen kind of comes up to when it says that you have LTE or data connectivity, that's the time that it's taking to get that bearer channel. So say that takes another 15, 20 seconds. At that point, you can easily be at a minute of time to get connected. Now we have a data session. Depending on how your data sessions are being set up, if you're using IPsec, we have to set up the IPsec tunnel. That takes milliseconds to a few seconds. If we don't finish the data session, or once we finish the data session, then we have to reestablish the DMP session. And DMP is not the fastest protocol. It's usually polling on a 4 to 5 second interval. It can take 15, 25, 30 seconds for that to work. And then all of that has some variability, and we might have to repeat some of those steps or have some challenge in that process where it experiences those numbers. So all of those things together add up to change that. Now, to your point about the dual modem devices, the dual modem devices are typically faster because they can be dual attached at the same time, and they can already have that data session, they can already have that barrier set up, and they don't have to go back and forth as much. So does that answer your question? I don't know that it gives you all the gory details of why these modems did this. Afterwards, between sessions, if you walk up and nicely ask Jeremy or Lishan, the testing crew, they can show you all the screens and look through all of the details. At one point, I wanted to run a plotting tool that would show you all these things, but that just wasn't working as effectively as we will learn things and do things. And I would like your guys' feedback on what should we be testing in future Plugfest. We plan to dig deeper into specific topics. Like we're not testing gloss and making sure, like we want to get to those things. We want to do more meter under the glass testing, things like that. But this is what we can get done in 5 months. So if you have a question or comment, or who's just enjoying the show, there you go. Okay. At this point, what's that, Mike? Okay, we are done with this testing session. We're going to try to get another speaker. At 12:30, they are serving lunch, I believe, out in the hallway. So we will be starting to serve lunch. I'm going to give Motorola, if you guys are ready. Yeah, we're going to go ahead and accelerate the schedule. And we're going to have Motorola show their demonstration. They're going to spend about 20 minutes here, 30 minutes showing us exactly the configuration with multiple carriers within that 3 megahertz of spectrum and how they're getting all of their various devices. We're going to see their IP camera running over a bearer. We're going to see a narrowband IoT session running at the same time, as well as a DMP session as well. So they're going to connect to the WebEx and they're going to get set up. They're also going to show you some spectrum analyzers on the screen and some of the gory details of how it operates and how these things work on. So, you guys ready to start? I'll get you a microphone. Okay, I'm going to hand it over to Gino to share what they're doing here. And I'm going to turn my mic off and sit down for a few minutes and drink some water.
All right, thanks, Matt. Awesome. So I'm Gino Soprano. I'm with Motorola Solutions, and we're going to show you a multi-carrier demo. And what we hear often is that 3 plus 3 megahertz, that's not a lot of spectrum. But we can actually, it's quite enough spectrum for what utilities need to do. And in fact, we're going to show an application here where we can have 3 separate applications working on a single 3 megahertz carrier. And what we're going to show is that there are 2 1.4 megahertz carriers and a narrowband IoT carrier that's operating in a single 3 megahertz band. And we're going to be showing a streaming video running over one of the 1.4 megahertz channels. And then we're going to show a ping application that's running over the narrowband IoT channel. And then we're going to show a full download on the other channel. And the full download is going to be stimulated by a tool in the UBBA that's called Other Channel Noise Source, or OCNS. So we're going to turn on OCNS on our third carrier. So as soon as we get the spectrum analyzer showing on the screen, I'll point out the channel configuration. So Marcelo, can you put up the spectrum analyzer view? And while Marcelo is doing that, I'll just point out that the video stream is going to be coming from our visual on camera. That's an IR and an optical camera. It has a 4 megapixel resolution. And if you wave your arms, you should be able to see some kind of motion in the screen there. And I see it's very difficult to see on the screen the spectrum analyzer, but I'll try to point out that the channel on the left is one of the 1.4 megahertz channels, and this one's carrying the video stream. But the little bump in the middle, it has a little bit higher amplitude. That's our narrowband IoT channel. Oh, now it's looking better. Thanks. And the channel on the right is carrying the other channel noise source, which is the fully loaded cell. And you can notice that green line is a little bit higher on the right than it is on the left, the average on the left. And the reason is we're transmitting full power on that channel. So we're trying to simulate that channel carrying maximum capacity. So the channel on the right is maximum capacity. The channel on the far left is carrying video. And the channel in the middle is doing narrowband IoT. And what we're showing is the pings, once they come up on the screen, there we go. The pings running over the narrowband IoT, they're running just fine with no loss. They have quite a bit of latency, but that's a function of the narrowband IoT.
Yeah, can we talk to people about what the latency? I think a lot of people ask how much data and what is the latency over narrowband IoT? Because in cell modem terms, we go, oh man, it's only how many kilobits per second do you guys see?
About 10.
10 kilobits per second. And oh man, the latency is
well,
50, what are we getting, 77 milliseconds there? Those all seem really high, but just put that in perspective of how much work we can do for a system on that amount of spectrum. I would argue you can run metering very effectively on that area. You can run all kinds of field communication devices on that amount of spectrum. Does anybody also see on there what's so advantageous about narrowband IoT? Coverage. If you want to put, and we've done testing where we're putting narrowband IoT 10 feet underground in sewer manholes to monitor water flows, and we're putting the modem, not the device with an antenna up at the surface. We're not putting it on the surface. We're putting the modem down in a manhole, working. We're putting them inside of metal enclosures, so no, like in a control panel, we're just putting the NB-IoT modem in there without an external antenna, and we're able to get communication connectivity to it. And when you look at throughput and latencies, if you're there as a human trying to do something, this can be incredibly maddening for you. If you put in a system that's trying to bring in data or do controls, that's doing it for you in the background, it can do that so much more effectively. And this can really be the technology to get the punch and the power. And one of the concerns that I've always had is, hey, if we do metering under the glass, how are we going to reach out and talk to every last meter? Because the great thing about mesh networks is if you can't talk to a device, you just add a repeater and I can talk to the next device. Great feature. The downside of that is every time I add a device, I double the latency and cut the bandwidth in half. You do that a few times, it gets down to these kind of numbers in your mesh network. The disadvantage to an LTE network in that scenario is I can usually give you broadband, but what happens if I can't talk to that one device? What do I have to do? Same thing, I have to add another node to the network. Now, what's another mesh node cost? 30, 40, hundreds of dollars. What's another E node, B node cost? There's some small cell ones that are more cost effective, but thousands, tens of thousands, hundreds of thousands of dollars. This is the technology that allows us to have this simultaneous ecosystem. This is the technology that allows us to have a device and have a singular deployment scenario. That means I can go take one of these Motorola radios and say, hey, Mr. Lineman, go put that thing up on the line, wait 2 or 3 minutes, the green light's gonna come on. If the green light comes on, you can go down the road. In the background, I could have just connected you to 4 or 5 different communication networks and made sure you had reliability and not have a whole bunch of different scenarios where you had to figure out, oh, this didn't work. Oh, mesh didn't work. I'm going to do this. Or LTE. We can get rid of all of those scenarios. And that's how LTE fundamentally feels different. So sorry for butting in or providing a lot of good color commentary on why. But the reason we get some of that punch power, narrow carrier, higher signal amplitude, that's where part of that that comes from. And then I'd also like you to talk about why, when you look at carriers, does the one on the right look so nice and clean? Because you kind of, I won't call it a trick, but you're doing something unique that we don't see in the real world, versus the one on the left, as we're actually digging into this technology. What do we? Why is it so much more jagged? And what's going on there? Tell us, dig into what's going on there.
Okay, thanks, Matt. Thanks for that color commentary. Very, very helpful. So the reason that the trace on the right looks so clean is because we're always transmitting on all of the resource blocks that are available in the channels. A resource block is the fundamental, it's the element, it's the subcarrier that actually carries the data. So with LTE, every channel is composed of multiple subcarriers, and every subcarrier is like a minimal, itty bitty channel. And that itty bitty channel is aggregated together to create the larger channel. When we're transmitting full power, all of those subchannels are being used simultaneously, and you get that very nice shape on the waveform. But on the left, because it's carrying video, the video traffic, the bandwidth varies depending on what's happening in the images in the scene. So we're not getting full power all the time on that channel on the right. What we're seeing is actually the video variation. So that's the difference between the left channel and the right channel.
So I want to add a little bit more educational and common commentary to what a resource block is, because I think this is one of the fundamental things to learn about this technology versus some other ones. It's not that different than what we're used to in narrowband communications, in the sense that we're used to having a carrier. Say we have a 25 kilohertz carrier for some sort of data transmission over LMR. LTE is very similar to that, except for now the subcarriers are 250 kilohertz each. So we've taken that 1.4 megahertz, divided it up into a bunch of 250 kilohertz subcarriers, and then that gives us frequency domain. And why do we do that? Why don't we just broadcast one large wide carrier? You want to answer? You don't need to answer. Well, it's one of the ways that we mitigate interference. If there's interference on a little slice of that spectrum at a time, we only killed off that little bit of data, maybe 8, 16 bits, there's different modulations, different things, just a little bit of data that is in that time slot in that time. So we talked about things in the frequency domain. We're going to give everybody a full lesson in OFDM here. We're describing orthogonal frequency division multiplexing. So we've talked about the frequency part of it. Now I'm going to talk about the orthogonal part of it, the space and time. Every, I don't know, 125 microseconds, is that a LTE symbol, something like that?
Oh, symbol time, yeah, sure.
But there is, in time, every few hundred microseconds, there is a new symbol of data that's being transmitted, and you see that integrated over time. That intersection of frequency and time is called a resource block. Most of those resource blocks, this is one of the things that you can go in and optimize. This is one of the things that we do fundamentally differently when we set up a utility network versus a carrier network. In the utility network, we're usually focused on speed, latency, and reliability at the expense sometimes of throughput. We're not trying to optimize and get every last bit out of this typically. We're trying to optimize and get as much coverage and reliability out of it. And that's just fundamentally why when you set up a private LTE network, you can do it fundamentally differently. This is also why some of the very unique aspects of why this interoperability testing is so important. We're using band 8 here in this case. Does anybody know what is unique about band 8 and Anterix configuration here in the US versus the worldwide standard? The up-down frequency duplex is different. And so that's one of the things that we have to make sure the devices support appropriately to successfully transmit. So with that, I'll
I'll hand the floor back over, continue your demonstration, but you're giving great demonstrations of some of the detailed insights of what's going on in the spectrum.
If we look at the other end of this, so we were talking a lot about the radio side of it and what all the nuances are of these multiple channels, but on the network side of things, in this configuration, you can actually assign each of those channels to a different core network or a different application. So you can share equipment, as an example, of a site can be shared across multiple operators. So that 3 megahertz can be subdivided, and multiple utility operators or operating entities within the utility can share that spectrum, but have their own channels within that 3 megahertz band. So that's one of the other nice features of being able to have multiple carriers within a single band. Let's see what else we're going to say here. I think that's probably it. And you know, the video quality. So if I can get folks in the audience to kind of wave their hands, and if you look at the video screen, you can see what that looks like. Yeah, that's not so bad. I know it's a small screen, so I apologize for that. But yeah, I think that's it. So any questions from the audience on this?
How many narrowband channels can you do with 1.4?
Okay, so I don't know that there's a standard limit, but we can do up to 4 narrowband channels in a single 3 megahertz channel. So we could do 4 narrowband channels and the 1.4 on a single 3 megahertz channel.
Yeah, I think the key thing that we're showing here is tight enough filtering so that you can put the narrowband IoT channel in the exact adjacent spectrum space without putting a guard band. A very typical deployment. If we were to map all this spectrum out across multiple carriers, if we looked at this, so you know, we could put the spectrum analyzer and go look off at T-Mobile or Verizon's network here. You can see they're usually broadcasting fairly wide channels, like 20 megahertz wide channels, and they're usually putting at least 250 kilohertz, if not more, between those channels, depending on what's adjacent to them. And we've absolutely seen this testing. Maybe I'll loop Tim into a little bit of this. When we've tested some narrowband stuff, like some 700 megahertz channels where we're using different radio technology, not OFDM, next to carrier technologies, depending on how kind of compatible they are in the frequency domain and working with each other, we have to put more guard band spectrum in there. And that spectrum is effectively unused. The nifty trick here is traditionally, if we were to set this up in most systems, that narrowband IoT channel would just be used for spectrum protection and you would get nothing out of it. So now we're adding that narrowband IoT carrier in there, and you're actually able to use that data transmission in that space and make some effective use for it. I don't think you're going to put 3,000 reclosers on that narrowband IoT channel, so you're probably going to run out of capacity before you do that. But wouldn't it be nice to go talk to those 15 meters that wouldn't connect and they have the same modem underneath it? They'll connect on that channel. They'll work just fine. If you can connect to a wider band channel, you connect to the wider band channel. But I'd also like to give a little bit more color commentary on schedulers, because this is another thing. We talked about that space in time. We need to talk about once data shut your mic off. With schedulers, we need to talk about how in time that we go about making the decisions about what we're going to put onto the network. So we had all those subcarriers. We have all these time slots in time. If you look at this on some spectrum analyzers, they'll show you the waterfall, is what they typically call that. That scheduler is another very important part of the configuration and the discussion about where we change things and do things differently for utility operations versus commercial network operations. And what that scheduler is controlling is, say you have data to transmit, the data comes in on the Ethernet port, gets held in a buffer, and then that scheduler sits there and looks, and it's running on the base station. It's getting information from all of the UE devices about what data needs to be transmitted. So it understands, hey, there's a video stream going on there. And in this millisecond, that JPEG or MPEG stream needs 400 kilobytes of data needs to be transmitted right now. So there's 400 kilobytes, and this UE's got 10 kilobytes. There's all kinds of different queues and depths of queues, and there's a million different ways you can go about
scheduling how that data is going to get soaked up from all the UE devices up to the master station, then ultimately sent on. The net effect of that is it has a significant impact on the latency of the channel, especially during some specific scenarios. What a lot of people don't realize, if I'm attached to the network but don't have anything to communicate, I tell the scheduler in the base station I don't have anything to communicate, and it will actually take me out of the schedule. If I then need to send some data, I can't just start burning out data. I have to wait till an open period where I can tell the scheduler I need to transmit something. Then it will get around in the queue and come and ask me and assign me a time slot and a frequency subcarrier which I can transmit. That is great for being efficient use of the spectrum. It can cause relatively high latencies if you're initiating a new session. You might see this if you're sending high frequency, and it does this in milliseconds, but if you're doing high frequency pings, you might see that the first ping takes 3 milliseconds, or the common complaint or misconception is, man, the latency on LTE is so high. Well, it's high, yeah. You're pinging across, it might be 50 or 60 milliseconds, but why is that? Well, some of it is here, it's low latency because the antenna, the UBBA, the EBC, everything's close, and it's all wired together. If you're on a commercial network, I know through some of the work that we've done with Verizon, if I'm here in St. Louis, depending on which core they're running on, Illinois, Missouri, and Kansas all share 2 redundant cores. One of them is in Kansas City, one's in St. Louis. I could have a packet that is going from Eastern Illinois all the way to Kansas City and back, and I can't cheat physics going through the fiber. That's part of your latency. Another part of your latency is this scheduler. And people say, well, why is 5G faster? Well, one of the things that we've messed with is we've optimized how that works. We said, oh, you can do local breakout. You can get out of this bearer channel and communicate to the local router at the EBC or at the UBBA instead of at the EBC. That's one change. And you can also change how that scheduler goes about fundamentally scheduling some of the data. It doesn't take as long. The industry has evolved forward in 10 years about what we expect. And they did that so they could do really high frequency feedback loops for like robotic process control and other things. They fundamentally changed that structure. And so those are all of some of the gory details of the differences between 4G and 5G. It's not just 4 versus 5. Okay. You got anything else? Thanks for that great demo. Thanks for your time. Appreciate it. Showing the gory details. I'm next going to call on Joe from 4RF to come share a few more details about their UE devices. But we got 2 4RF Joes. I wasn't specific. I should have said Joe McFadden.
Slightly above average Joes. I'll say this, 4RF is extremely honored to be here at this event, and we are very much looking forward to Plugfest 2, 3, 4, and so on. So I really appreciate the invite. And I do want to mention and just reiterate what was said about the Novatech folks and the Cisco folks that are up here working. Gosh, Jeremy, Sean, Dan, and those guys, to say they worked hard was an extreme understatement. These guys worked on very little sleep, and I'm pretty sure there was an uptick in Starbucks and Red Bull's stock price because of those guys. So it's been extremely appreciated for that. So anyway, like I said, we're happy to be here. We love the 4RF Aprisa LTE. It's an extremely robust device. In addition, it's pretty obvious. You'll see that it's got an aesthetically appeasing, sexy chassis compared to everybody else, right? So that doesn't mean much, but again, we're happy to be here. Thank you very much for the opportunity. And if anybody has any questions, you can spot myself or Joe.
Yeah, well, I'll echo what Joe said about being here and being part of the Anterix whole ecosystem is great for us. We're very happy to be there. As Joe said, we brought if you're familiar with 4RF, robust is like our middle name, and all of our stuff is designed to live in that environment, to live in, to live in that environment. So we studied a lot and talked to a lot of customers out there, and we've always done that before we develop things. We don't do the, build it and they'll come kind of thing. And we like to focus on what our customers told us they wanted. So we spent some time getting this box ready. Some comments from people, hey, 2 years ago it looked a lot different than it looks like now. So it's come a long way. invested heavily in it. We think we've used some leading edge technology as far as the software is concerned, but also hardware wise. If you come by our booth, pick it up, and you hold it, it's different than others. It looks like it comes along with our licensed product as well. So I'll give Joe a compliment. I judge some devices by whether or not I would use it in a fight. And I think I would use Joe's device as a weapon in a fight. That's one of the criteria for picking UE devices is how does it feel? But I'd also give you a compliment. I've always been impressed when I've logged into many different UE devices, the cleanliness of the user interface, the clarity of the naming and how they name stuff. I say it doesn't have any jank factor of things that I'm like, like, hey, we want to go to Band-Aid operation. They'll put a nice checkbox that says 900 megahertz operation. You can check it instead of saying, please type in the frequency range at which you want to transmit on, which achieves the same result. But, oh, and by the way, you got to write that out in hertz. So it's, 900 megahertz is, 6 digits long, and you got to make sure you get the zeros right. So, we appreciate that. Thanks for participation. Are there any questions for Plugfest at this point with two Joes? Okay, without any questions, we're monitoring chat. There's not any online questions on there either, is there? Okay, well, if you're online, feel free to ask a question as well. At this point, it is lunchtime. Lunch is served. I've seen it filtering around the building. I believe it is out in the hallway where we had breakfast. Grab some lunch at 12:50. I guess they're telling me it's in the next aisle over. So check out the vendor demonstrations, check out some of the active devices here in the demonstration area that are attached to these cores. We're going to move and start at 12:50 back in the grand ballroom where we will be seeing continuing Plugfest with demonstrations of the Anterix Active ecosystem and the demonstration devices that they have. Mike and Jim have got a great set of demonstrations of all kinds of different field devices. So please join us 12:50 Grand Ballroom. We'll keep the WebEx open, but we'll just have a placeholder slide in the meantime. So enjoy lunch. Thanks everybody for joining. Hope you enjoyed the first session. We'll keep this going today and tomorrow. Talk to you later. Bye.